Find the domain of the following vector-valued function, writing your final answer in interval notation. So just like with limits, it's going to be easier to think about the domain of each individual component of your vector-valued function, and then afterwards take the intersection of the three domains. So that's how we're going to approach these here. So let's start by thinking about f of t, which is defined as the square root of 64 minus t squared. Now, if you're comfortable, go ahead and work through this quicker. I'm going to go through just a tiny bit of review here. So we recognize this function. This is a semicircle. And if you didn't recognize it, you do now. So this is the square root of r squared minus x squared, where r is the radius of that semicircle. And so if we think about this graphically in the Cartesian coordinate system, we of course know here is, well, sort of a squished semicircle, but there's your negative r value and your positive r value. These are the values of your domain. So we can see from looking at our semicircle, or we recall that here x is an element of the closed interval from negative r to positive r. So looking at our function here, we see that we have the square root of 8 squared minus t squared. So our radius is 8. And so we can say that therefore, t is an element of the closed interval from negative 8 to positive 8. So this is the domain for f of t. And now similarly, we want to do the same thing for g of t, which is defined here as the square root of t. So here we just have a square root, and we of course recall that with any even root radical, we always want the radicand, or the inside, to be positive or greater than or equal to 0. And that's it. So we can say here that the domain is t is any real number greater than or equal to 0. And last but not least, we want to do the same thing for h of t, which here is defined as 3 divided by the square root of 3 plus t. And so this is similar to g of t, except notice that your square root's in the denominator. So here we set the radicand 3 plus t strictly greater than 0, because we know division by 0 does not exist. So this lets us know that t, in this case, must be strictly greater than negative 3. And so therefore, t is an element of the open interval from negative 3 to positive infinity. So we have the domain of each component, and to find the domain now of the full vector-valued function, we need to consider the intersection of these three inequalities, or intervals. So we need to find the intersection of these three domains. So you can even think about this as the full domain is going to be the intersection of the domain of the f component, intersected with the domain of the g component, intersected with the domain of the h component. So we're looking for the common domain amongst these three intervals. So here we go. We have the domain is the interval negative 8 to positive 8, and we're intersecting this with the interval from 0 to positive infinity. And then we intersect this with the interval from negative 3 to positive infinity. So let's consider these lower bounds here. So what is the smallest common bound? 0. So we can say that the domain has a lower bound of 0. And now, what about the upper bound? Well, g and h extend towards infinity. Notice that the domain of f stops at 8. So that's going to be the upper bound of our domain. And this is our beautiful final answer. This is the full domain of our vector-valued function. Now, if you haven't seen this in a while, sometimes it can be helpful to think about a number line. So here's a good old-fashioned number line. We, of course, know that as t approaches the left-hand side, that's negative infinity. As t approaches the right-hand side, that's positive infinity. And all we need to label on this is the focal points. So say there's -8, there's -3, here's 0, and here's 8. So I'm obviously not doing this to scale. And to find the intersection, you want to think about where do these three domains lay on top of each other. So thinking about the domain of the f component, we know that's from -8 all the way to +8. Now, thinking about the domain of the g component, that is from 0 to positive infinity. And then last but not least, thinking about the domain of the h component, this starts at -3, but we have a hole at -3 because t cannot equal it. It can get infinitely close. And then the domain extends towards positive infinity. So where is the common domain? Where do these three domains intersect? They're only intersecting from 0 to 8. So this is confirming to us that t must be greater than or equal to 0, less than or equal to 8. So this is your inequality form. And we then take our inequality and convert it to its interval notation.